Well, good morning, everyone. You're here for the weekly webinar at EasyPower. I'm Chris Duffey. I'm the principal engineer here at EasyPower. And today's webinar is an introduction to dynamic stability. And we're going to be looking at this with a real kind of, 30,000 foot level. We're not going to get into a lot of details, but we are going to talk about stability, its basic functions, how it's going to work for you, what it can do for you in your simulations of real-time behavior in your power system. So I'm going to do two things. I've got a set of slides here that I'm going to go over first. And then after this, we'll jump into the software. Now, obviously, we're going to be using EasyPower to look at these examples. And there's a number of nice features in EasyPower that help you do dynamic stability simulations. But the principles that I'm going to go over in the slides really carry across any software package that does dynamic stability. My background before coming to EasyPower, I worked for 10 years in upstate New York at Power Technologies, Inc., PTI. And if you have any familiarity with the PSSE package, you'll understand that is a large-scale simulating tool where you can do 50,000 bus dynamic stability simulations of the entire utility power grid. So that's my background. I worked in the utility system performance group there. And then after coming to EasyPower, after working there for roughly 10 years, we put together a dynamic stability tool so that we had that feature in EasyPower as well. So let's start looking at these slides. And first off, dynamic stability simulations have been around for more than 40 years. When I was at PTI, I would say they'd already been doing it for 10 or 20, and that was roughly 30 years ago. Dynamic stability simulations are a proven method. They are used worldwide right now. Like I said, the PTI software in its day really was the top tool, period, in the industry around the world. I can remember traveling and teaching training courses on that tool. I traveled Bahrain, Tunisia, Australia, and taught those training classes. And the software was really expensive. I mean, we're talking, $50,000, $100,000 a license. So it's definitely proven. People have put a lot of money there. It assumes we're interested in a time response that's no smaller than about half a cycle. It assumes we're not interested in fast sub-cycle transient effects. And unfortunately, the word transient has found its way into dynamic stability as well. We talk about transient motor starting, and I understand the reason for that because we call the field winding the transient effect in a generator. But the term transient really should be relegated to fast sub-cycle things that you would use for like running analysis with the EMTP or the electromagnetic transients program. So we're not interested in those. We're looking at things with more of an RMS response about every half cycle. It also assumes we're interested in the time response of machines, that is generators and motors, and their control systems. Now, what can EasyPower stability do for us, or any package if it has similar features like EasyPower? First thing is, and we talked about this in a previous webinar, it shows us the many forms of motor starting impact on a system and the impact on the motor itself. We can simulate sequential motor starts, that is one after the other after power recovery on emergency generation. We can simulate isolated system behavior with frequency depressions and load shedding. That's very common for a lot of people with cogeneration. We can show protective device tripping on faults and contactor dropout from voltage events, which, that could be a sag on the utility, that could be a motor starting event or something else happening in your facility. We can evaluate things like fast bus transfer, which is switching motors very quickly over to an alternate source so that we can continue pumping of motors, especially for like nuclear facilities. And one of the key things we need to look at there, look in that type of a simulation, is the transient shaft torques. So we can use it for that purpose as well. We can show impact loading effects on backup generation. You have a backup generator. what does the load impact actually do? How does the voltage depress? How does the AVR respond in real time? How does the governor pick up the load? We can reveal dynamic instability in a system with multiple generators. I'm sure from school and some of your background knowledge, there was that case we automatically had put in front of us, which is you had two generators with an inductance in between them, or a reactance, because we were looking at things at some system frequency like 60 hertz. And we could evaluate when we would go dynamically unstable, where we couldn't keep stability. We didn't have enough synchronizing power between the two generators. We can show critical clearing time. In other words, how long can the fault be on before my co-generator, basically after the fault has been cleared and now our system is trying to recover, but the co-generator has already accelerated too far and it just can't turn around. So we can determine critical clearing time. We can simulate. This is an interesting feature that I'm going to hit. That's one of the last things I'll talk about today, and I'll show you with EasyPower, is that if you're really interested in detailed arc flash and knowing how the currents respond over time as motors decay, as generators decay, as protective devices open, not necessarily at the same time, you can do that with the EasyPower Dynamic Stability. So arc flash, the detailed form of arc flash, and we'll show you the amount of energy produced in the message log on that. We can confirm proper excitation system and governor system tuning, which is really data evaluation. You're going to perform a study in dynamic stability. Well, is the data that you received any good? Definitely you'd want to check that out. That's one of the first things that I do when I'm performing any type of stability analysis for a client. And when I teach my stability class, I go over that's one of the key items. How about performing data tuning simulations? Let's say you actually have some stage tests. You actually had someone go out and tune up your excitation system, and they show you the open circuit step test. Well, you can run a dynamic simulation and overlay those curves in Excel. Just copy the data out of the program, put it in Excel, and overlay to see if you're matching. So you can continue to tune and get it tuned up to match the actual response that you're seeing in the field. You can evaluate plant internal voltage depressions. That is, something's happening on the utility grid. How is that affecting voltage inside my facility? A couple interesting things here that we'll also look at today that I have really not seen in other stability packages, and that is we can help you predict fuse fatigue and how far relays are traveling for a given condition, or for like a fault condition or some type of switching condition in a facility. Maybe devices are racing, and you want to know how, which one's going to trip first, which one has that chance. We can, that was this item, show protective device racing under fault conditions. Next, we can use stability, the power flow, right when we enter stability, and we'll talk about that. The power flow solution will give you higher accuracy in terms of how induction motors respond to voltage conditions and the VARs that they draw. That's a really interesting thing there. We can simulate governor mode changes from droop to isochronous control. This often happens when you go into an isolated mode. A generator or a governor system on a generator will change its mode from droop to isochronous control, so you can see how it responds. You can discover if your backup generation responds to automatic transfer switch action, how it will handle it during the transfer of load. And, I could go on, and I'll just stop at this point, but just say that there's many, many more real-time simulations that we can help you with in terms of discerning the response of your electrical equipment in your network. Many, many more, but we'll pause there and not continue with the descriptions of what it can do. But how does it work? Yes, okay. 3 main items here for how does dynamic stability function. First, we're using proven modeling knowledge. This is not new. These models, the foundations for these models, this is not new theory. It's been around for 50, 60, 70, maybe even 100 years, okay? So We're using proven modeling knowledge of machines and control system behavior to simulate a real-time electrical system response. The network, that is cables, transmission lines, transformers, busway, etc., it links the models together in a common three-phase balance domain. Just note, EasyPower Dynamic Stability is a positive sequence three-phase balanced simulation. We're not doing unbalanced. At this time, we're not doing unbalanced. Finally, it uses the method of numerical integration to progress us systematically through time. So the models are built and function modularly. They respond to clearly defined inputs and outputs. They react to the network via their terminal conditions. That is, the generators, excitation systems, governor systems, motors, and motor loads, they react to the terminal conditions. Protective devices, ATSs, contactors, those react to network conditions such as flow over a branch or over a line or through a transformer or bus voltage. The types of models that we include are generators, excitation systems, governing systems, motors, motor loads, all power protective devices. So if you've entered them, they're going to be made available to you in dynamic stability and they will perform their function. In addition, we added contactors, automatic transfer switch, over-under frequency, and over and under voltage. So this gives you an idea of the generator system model, for instance. So we're looking here. Let me get my mouse up here. This is the machine. This is the rotating machine. So we'll call that the generator. Over here we have the governor system, which consists of actually two components, which is the governor and also the prime mover is included in that. Over here we have the excitation system, which can have an amplifier, an automatic voltage regulator, an actual rotating exciter, an alternator. We're going to bundle that into the excitation system. And finally, if you have a power system stabilizer, we're not going to talk about those today, but if you did, they would interact here going into the excitation system. Notice how the interactions are. We have field current being fed back to the excitation system, field voltage being supplied to the generator, mechanical power from the combination of governor prime mover feeding a generator, speed coming back and feeding the governor model. And then we link with the network here. And we link through a Thevenin equivalent impedance and a Thevenin driving voltage. So the model produces the voltage impacts the network. Similarly, for motors, it's pretty much the same exact model and connection with the network, except it's a slightly different internal model. Induction motors don't have a field, for instance, so they don't need that AVR or any type of the excitation system, but they do have a load. So we have a new component over here, which is the motor load. Torque goes into the model for the induction motor, the machine, and speed is fed back to the motor load model. Now, all machine models, generators, motors, include frequency effects. So if the frequency it goes up or down, it will affect the model. Voltage effects, saturation, and inertia effects. In other words, the speed up and slow down of equipment. The network is basically our foundation. It's the connection between all of the machine models. After it's solved power flow style, that is, with this, like in power flow focus with a swing bus, after it's solved power flow style, it is used for determining all of the initial conditions when entering DS. So all the machines extract their terminal conditions of power, real and reactive power, to initialize the models. It's used for the input of all protective devices because, they need branch currents, they need transformer current flow, they need these values to have an input so they can perform their real-time action. And it's used for all scripted, script being some statements that we can write to perform a simulation in particular order, for all scripted and automatic, that is, if a breaker trips automatically, switching actions. So if it's either scripted or it's automatically performed, the network, through breakers switches, low voltage breakers, high and low voltage breakers. That's how the switching action is performed through the network. The network is the thing that connects everything. Here's a kind of a general slide picture to show it, and that is, you can see on the periphery of the network. That's how I've drawn it, because it's, you know, we're looking at kind of a 2D slide here. So on the periphery, I'm showing the generator, the motors interconnecting through a Thevenin component that's inside the network. Then we have our transformers, we have our transmission lines, our cables, we have relays, we have breakers, high voltage breakers, low voltage breakers, contactors. All of those components are in the network model, and then the generation and motor system models impact it from the outside. This is how we progress through time. So if we basically define a D state, and this is, again, I picked this up, this is kind of a PTI method of stating things. It's also, if you're familiar with a gentleman by the name of Paul DeMello, who is one of the key top engineers in the world for simulating or for performing dynamic stability simulations and coming up with modeling methods. This is kind of his method of presenting numerical integration, and that is, if we have a D state, that is a change in a component condition of a model. So it's a measure or a calculated number of what's changing. And then if we have a state, which is really the present held condition at one moment in time of that same component, then the state in a future moment is equal to the state of the present moment plus the D state times the time step of your simulation. And this is basically the Euler method of integration. And it's the method by which we're going to progress or march through time in a dynamic stability simulation. So the overall process kind of looks like this. We're entering dynamic stability, and all of this is going to be done to set you up for a simulation. We solve the swing network. We convert the network over to a Thevenin model. We take all the terminal conditions and feed them to the models, then we initialize them. Then we're all ready to go. But just a little clarity here, I didn't put one loop I probably should have put in here, and that is, this is really iterated here, because induction motors throw a little wrench into everything. What their terminal conditions not only, you know, are defined for the power flow when you come in, but they're also defined by the machine equations. So the VARs on the induction motor, if you want to get a more accurate presentation of the VARs, just take your case, add some some motor models, some typical ones from the library, and just enter dynamic stability focus, and you'll see how the voltage more accurately affects the VARs being drawn by the motor. So we iterate this first initialized dynamics loop to get the induction motor settled properly. It also means that the power flow solution after entering stability is different than what you would have in a regular power flow simulation. If you scale a motor, for instance, in power flow, it scales both watts and bars down. That does not happen in dynamic stability because the scale factor is applied to the mechanical load on the shaft. So your VARs are not necessarily going to drop. Once we've initialized, there's your D state calculation. We calculate what's changing in the system, then we integrate it. And literally, the integration routine is just a little bit more. There are several forms of integration routines, but it's basically this same form, just one step more slightly one additional step in complication to get our integration. It's called a modified Euler method that was developed by DeMello. And so after integrating, we update some model variables. We then send the Thevenin voltage, that is the model condition, back to the network. Then we solve the network. So this tells us something. The network is solved on every time step. That's one of the most time-consuming components of a dynamic stability simulation, especially if your network gets large, 500, 1,000, 2,000 buses. Every time step, it's going to be solved. So after we solve the network, we check for any switching that has to be done. And before we continue, we perform it, and then we solve the network again. Then, after we've performed any switching actions, like due to a breaker tripping or due to a script saying, hey, open a breaker or close a breaker, then we take the network conditions, feed them back to the models, update our terminal conditions, save some results, increment our time where we happen to be because we just progressed through time by integrating, check to see if we're at the end, and then this loop is continued until we reach the end of our simulation. So that's the dynamic stability method in a nutshell. Now the quandary. So you've listened to me so far. Let's see how many, I don't even know how many minutes it's been. There's a number here somewhere, but I can't find it. So I've been talking for a while. So the quandary. Why do engineers tend to stay away from dynamic stability analysis? One of the key answers, yes, is, well, it's more complicated. Yes, okay, yeah. But in reality, I'll guarantee that you'll find in almost every case, it's the data factor. We need more data. If someone could make this easier for me to get data, for goodness sakes, I'd at least give this a try and to kind of see what's happening in my system. So data really is one of the big deals. Data for generators, excitation systems, etc. Consider this. How about data needed for just one generator? This is only part of it. Here's the other half, okay? So we've got I'm not going to read all these, stator winding resistance, leakage. We have all of the reactances that we've probably seen somewhere along the line. Then we have the time constants. And we have a D and a Q axis now. Oh, okay. It used to be just, give me one single Thevenin value that represents the short circuit capability. That's what we do for ANSI fault calculations. Well, it gets a tad bit more complicated here because we want to simulate the real-time behavior. And then not only those, but now we have saturation and inertia. It just gets even more complicated. What about the excitation system model? How do I even know what to do with this? What values, they're all listed here, am I supposed to come up with? Well, of course, my recommendation is get them from the manufacturer, have them tell you what model this is. This one happens to be in what's called an IEEE AC6A excitation system model. It's for a brushless excitation system. Just because of my background, I can tell that because of this section over here. This is a field current feedback section, which I know is in brushless units. Interesting thing on this model, if you ever feel like looking deeper, notice here there must be an amplifier that's fed right from the bus voltage of the generator because the terminal voltage is multiplied by the limit. In this particular model, if you fall, basically if the terminal voltage is faulted and it drops, you don't get anything out of this excitation system. It collapses right here. And there's other models where this doesn't happen, where that's what we call separate excited. But what do I do with this? And all these numbers here, and all these numbers. The same data issues that I just showed you here occur for governor systems, induction motors, synchronous motors, motor loads, and various other models. So here's our quandary. How do we overcome this if we desire to use dynamic stability to help us understand our electrical system behavior under dynamic conditions? Here's my answer for you. Now, you really should get your own data as much as possible, especially for machines. But if you don't have it, I'd say it would behoove us to at least use typical data values so that we can see what is the possibility of happening. If we haven't got it nailed down exactly, let's at least kind of get some simulations under our belt that give us some ranging of effects that could be happening on our system. And we supply you a host of typical data for every dynamic stability model in the EasyPower library. And I'm going to show you this. The value of typical data should not be underrated. It's a known fact that using a typical exciter model with well-tuned typical data is better than not modeling it at all. I mean, when an excitation system or the AVR is tuned out in the field when it's commissioned. It's tuned to meet IEEE overshoot criteria, for goodness sake. I mean, they're not just going to walk away from the generator and not tune the excitation system. Well, see, I will have to admit, I measured one where somebody by accident walked away and didn't tune it, so we ended up tuning it for them. But still, I would say in almost every case, the excitation system is going to be tuned, okay, for the system where it's applied. This also applies to governor models. They are going to be tuned to give as good a response as can be achieved with that particular generator. Now, I know the generator data is something you should really be able to get your hands on. I hope you can, because it's one of the key components. But again, if not, you could at least use data out of the EasyPower library. We have a host of generator data already there, and it's already been sanitized, and we've already looked it over, and we've made sure that it really represents a real machine. Also, how about data that you already have? If you've performed an arc flash study or a coordination study, you have already entered your protective devices. Well, they already function in dynamic stability if you've put them in there. That is, I'm not a sales guy, but I would say you probably need to own Power Protector as well. So if you have Power Protector and you've entered your protective devices, they will function automatically in dynamic stability. Contactor data for motors. These are some of the simplest settings. You can add these very quickly. All you need is a dropout time and how long before it drops out in its setting. Motor. Now, we've kind of already handled this in a previous webinar. If you haven't, if you weren't online for that webinar, it's on our website already, and it's called Transient Motor Starting Part 1. And we've developed a method, and I explain it there, how to help you get induction motor data. We have a full flux model for the motor, and so because we have a full flux model, the data is not typically what you're used to, but we have a method all defined out, and it's shown in this webinar how to get that information from torque speed curve and some of the rated parameters right on the nameplate. Okay, but if you can't find any data, the least you could do is go into our library. We have already derived from manufacturers' supplied information over 40 induction motors. We validated them, and they're in the library ready for your use. So let's do it. Let's see how quickly we can add data and get some meaningful dynamic stability results. So let me shut that down, and I'm going to bring EasyPower up. And this is my example system. This is basically DS example 2 modified, so I could put this presentation together today. So if you look at it overall, I've kind of messed around up here on the high side, and I'll tell you why. I've got a co-generator here with some generator data. I've got a host of motors down here with motor data. I have an automatic transfer switch. I've got a standby diesel generator. So one thing before I jump into using this, I just want to discuss very quickly for yourself. This should come with the installation. It's the Dynamic Stability Reference Manual. A lot of the things I'm talking about are in here, plus details on all of the models. So let's make it so we can read it. We talk about entering data, modified equipment behavior, all types of things, time step issues, numerical instability things to look at in detail, how to write a script, how to do plots. I'm going to touch on that briefly, but if you don't catch it, as I'm going through it quickly, you can go and get the detail here. It should come right with your installation. If it didn't, just call up tech support and they'll send you a PDF file of this. And we talk about the dynamic stability methods and all of the different models. They're all discussed here in the Dynamic Stability Reference Manual. I believe it is over 300 pages long. There's a lot of material. Here for you. Okay, so what I want to do first is just Number one, remember I talked about checking data that you've already put in. Let's say I've done that on this generator, and I obviously have, and the way I can tell is because it has 3 additional symbols. It has a rotor symbol, a field winding symbol, and a prime mover symbol. So that means I have all 3. I have the machine, I have the excitation system, and the governor system specified for this unit. Upon entry to dynamic stability, it automatically solves the power flow, just like I told you, and all the models are now initialized and ready to go. So let's step test this. Let's step test the ABR here, and we see, oh yes, I'm getting a very decent response. I step it up, and the terminal voltage here, the cogen ET, steps up. It's got a little bit of an overshoot, and it damps out very quickly in about 3 seconds. Very good. Now let's step test the governor. This is a gas turbine. This cogen is a gas turbine. We see that we have some type of a limiting going on, but it comes up. This is the speed response of the unit. We get a speed dip and a little bit of overshoot here. And boy, it's within about four seconds we've stabilized after doing an offline load step test on our governor system. We can do the same thing down here. By the way, all I did was double click on the symbol. So I double clicked on this and I double clicked on that to check my data with open circuit step tests. I can do that on my standby generator. Oh, we got a really snappy AVR response here, which most co-generators, backup generators do. And we see that the governor response is, this one's isochronous. This one's not a droop. This is in droop mode. So in this one, the frequency dips and comes back to 60 hertz. Whereas in the other one, we had steady state droop. Oh, do you know what? Not this one either. This one must be a form of isochronous as well. But you could have it in droop mode if you wanted to. Droop mode means that with a step load and power, we would see the speed drop slightly. Okay. So I've done some step testing. Now let's see how quickly we can put some data in. I'm going to go back to database focus, and I have on purpose left motor M3 out. So I'm going to come here. I like to use the ribbon. If you want to, let's see, where is it? Home, window, view the equipment palette. If you want to pull off the equipment palette, you can do that. I like as much screen real estate as I can get, so I typically close that and work off the ribbon. So I'm going to take a motor. I'm going to put it on here. And I'm going to add a low voltage breaker. I'm going to make it just like this 500 horsepower, so I'm going to give it the same exact breaker contactor. And then I'm going to come in here and I'm going to say, okay, now I do admit 500 horsepower motor on 480 volts, pretty not realistic. I know, okay, just bear with me. These are examples. More than likely you're not going to get over 250, 300 horsepower. I know that, so 750 is almost a very unrealistic thing, but let's assume we have 500 horsepower motor, and I'm just going to type that number in. Short circuit, I'm going to hit calculate and get this number right out of the red book. Then I'm going to go to the stability tab. Now, if you already have a motor, you can pull the data right out, but if you're adding it, you can do it, just add that information. Notice in the spec tab, I just let these guys default because I'm going to overwrite them with data from the library for stability. So I'm going to go to manufacturer. I know all the low voltage models in the library are made by Rockwell. And then here we have all these names. So what do they mean? Well, let me do this for you real quick. I'm going to pop back to wrong thing. Where? Just a second. Let me go like that and bring this up here. Okay. Go down here for motors. Okay. So the way it's ID'd is model, induction motor or synchronous motor, IM or SM, the horsepower, 100, etc., synchronous RPM of the motor, the NEMA design code B, and the NEMA code G, for instance. So you can see how that's interpreted down here for motors in the library. This information is in the Dynamic Stability Reference Manual. So it's a 500 horsepower motor, and I believe, let's put that in again, and it's calling it M3. That's nice. We're going to enable it, manufacturer Rockwell, and let's get the biggest one we have, which is a 200. So this is kind of a blend of data that we're doing, but we'll just choose this one to get us as close as we can, and we're going to import from the library by clicking that button. And yes, we want to do this because we want these to match what's actually in the library for the stability data. We want a complete copacetic set of data. And so yes, we want to overwrite the spec tab with this information. Once we've done that, notice by default, we get speed squared characteristic. I'm going to leave this as default for now, because what this means is at 100% loading, I have 100% torque, but it varies by the square of the speed. When I have 0 speed, I have 0 torque. What's not complete? I bet you it's the short circuit tab. I forgot to hit the calculate button. Now we'll hit OK. So I just added a motor that fast by pulling data out of the library. Okay, that did not take very long. And again, to get some sensitivity analysis, that is, throw some motors on there, maybe vary a few things, with the motors that you select out of the library, and see how that changes the response on your system if you don't have the details yourself. So once we've done that, we can now go into dynamic stability. We can right-click. Okay, when you come in, it's solved. Well, the motor's online. Well, I want to start it. So to get it offline, we have a method, not a double click in this case, a right click, an open, and a resolve. Now the motor's offline. The entire network just resolved. You right click, said open and resolve. If you notice, these values changed up here. I'll do it again. I'll close and resolve. See, they're changing. It resolves all the initial conditions of the network. So we're going to say open resolve, and all we have to do is double click on the breaker to close it. And now we have a motor start. That fast. We can see the terminal voltage on the motor, which is 0 before it starts. Then it's applied. We get a voltage dip. We have the current, starting current. We have the speed of the motor, and we have the torque. And this is appearing in what's called the auto plot. The auto plot, if you close a breaker on a motor, it's smart enough to know what to plot. We have we can tell what each of the values are, each of the curves from this legend. ET is terminal voltage, current, speed, electrical torque. You can also turn on a data cursor and see values. So our starting current is somewhere around 6 times. We're dipping to about 94.7%. Our speed is obviously going from 0 up to a final value of 0.99128, which under full load we would expect to be the rated slip of the machine. Okay, and then here's the torque going through its starting condition. And finally settling out at rated torque of, yes, 1 per unit at rated load. Okay? So that's how fast it was to basically put that together. Put some data in, run a simulation, and get a motor start. Very, very quick. I know this is a little scrunched over here, but I had to fit all of this in a 720p picture so that when the video is saved, and some people have only 1024, 768 projectors that they display this over. So I learned a lesson in the past. So if this looks a little crammed, that's on purpose, just so we can get that over the internet to you. So we've done a motor start. When we're done, we want to reset to do something else. Well, we just reset our simulation with the reset key. So there you go. We have a quick addition of motor data right out of the library and a quick motor start. Now, if you noticed, I'm going to do this again. Notice how long the motor took to start. It wasn't very long. It's starting at 1 second, and it goes to, roughly 2 seconds. So it's about a 1 second start. Notice one of the key items for how long a motor takes to start is inertia of the machine. If you want to do some sensitivity, go back to the database, come into this motor, go to the stability data, find inertia, which is H, kilowatt second per kVA, and if we double it, this is linear. I'll tell you, this is linear. You double the inertia, it's going to take you twice as long to start. You can run to stability, open, resolve, double click, and you see, yes, indeed, we start at 1 second and we start around 3. Okay, there we go. So 3 minus 1 is 2 seconds. It took us twice as long to start by doubling the inertia. So that's a key value. You see, those are some key values in that data. But again, we're going to put typical data values in there for you, and we're going to put a typical inertia value. If you want to really get much closer, then you have to start adjusting each of those parameters to get it closer to what your motor actually is. Okay, how about something more elaborate? So okay, that's our first run. Showed you how to get some quick data in, how to do a simulation. Now I really want to show you the type of things that you can do with stability. If I want to kind of open eyes, really. That's one of the main things that I want to do today in this webinar. I don't want it to be, these are the details and the nitty-gritty. Okay, you can come back, you can talk to tech support, you can also listen to, for instance, for motors, you can go to that first webinar that I did on motors, and you can get some of those details. But let's look at what can we do. How about a sequence motor start? What if I wanted to start all these motors in order on this bus? I've already put a script together for you, and we have a script tool. I'm just going to show briefly here, where I have a script called sequence M456. And in here, I say, and I pick commands here to do. My command is run 2 times 1 second, close low voltage breaker BL4, run for 2 seconds, do the next one, run for 2, do the next one, run for 3. So I've edited that, put that in my script, and I select it right here, sequence M456. I hit run to run a script. Interesting. So let's take a look at these results. I have already, by the way, I've already made some plots for you too for this, for our presentation today. We'll look at that briefly right after this. So in plot 1, I've defined voltages. I want to plot per unit voltages on the switchgear 13.8, MCC 2, 3, and 4, and the utility connection. So here are all the voltages. You can see for that motor sequence how low the voltages went. Well, went down to, wow, on the green one, which is where the motor started, we actually went down to 87, roughly 87.9%. Look at the rounded characteristics. Kind of interesting. That's because other motors are supporting the voltage. Also, what about this thing? Why is the voltage pulling up prior to the start being completed? This is due to the AVR control action of the generator. It's trying to boost itself. We could actually look at the currents in each of the motors that we just did our sequence start. There you go. M4, 5, and 6. There's the currents. And here's also the amperes on the cogen unit during the start. Boy, this is really interesting behavior due to the response of the AVR and all the other motors in the system. Things are moving around quite a bit, aren't they? We step up and we step up, and here we go, a higher amount of current on the cogen unit. Notice also other motors are being affected. So M1 on a completely different bus, look at it, it's having a sudden drop in amps, and because of the voltage depression, its current is going up. So you can see all these things and how they're behaving in your system. Plot 3 is our cogenerator. I elected in this plot to put the terminal voltage of the cogenerator, its current, its speed, its mechanical power, and its field voltage. So you can see how the AVR is responding right now. Here's the field going up. The motor's already started. I kind of overboosted myself. Now I need to recover and bring myself back down again. So you can see all of these responses right here in different plots. And last, plot 5 here, we have for M1, M2, M7, and M8. That's the motors on the left side, MCC 2 and MCC 3 or 4, excuse me. These are the motors on either side. These are the medium voltage motors, and these are the other low voltage motors, and we can see how their current is being impacted by the voltage depression. Now, this is with the utility. What would happen if these were impacting the co-generator by itself? Now, I just want to point something out as I reset, that in this setup that I have done right now, we're basically netted out at the utility tie. So the co-generator is producing about 6 megawatts. And that's almost exactly the amount of load we have connected. Okay, so we're netting out here to almost 0. So the first thing that we do is we want to drop this utility source first, let the system respond a little, or kind of respond to it and settle out, and then we sequence the motors. And I've done that here in drop util sequence M456. All I have to do is run the simulation. If I look at the co-generator, I can see here I have a little, at this 1 second, when it performs its first, opening of the utility breaker, I have a little bit of a speed change here. So now I'm on the co-generator alone. And because the co-generator is supporting all of these motors and all the loads on this bus, we see an even more drastic behavior in this voltage response because of the AVR. We see a dip, then the AVR really working hard, here we go, pushing itself up, trying to respond, and we see once the motor has released its start, we have a significant overshoot up to, and let's put this over here, we're dipping down to, this is on the co-generator, so this is at 13.8 kV. For this system, we dip down to under 90%, just under 90% at 89 something, and then we overshot 107, so that means we're 107% voltage for that brief moment in time due to a motor start. And this is a very, very common behavior. I've done measurements on large ships that have isolated power systems. I've seen these responses on voltage show up on the bridge, on the 120 volt outlet, because some large motor was starting over and over and over again. Instead of putting it on a drive and controlling its flow, it's on a start. They have it on a, well, start it, then stop it, then start it, then stop it. And I saw that happen repeatedly up there on the bridge. But this was affecting every power outlet, everything on the whole ship. So this is a response that's seen a lot for isolated cogeneration or just isolated generation, and then how it responds to a motor start condition. Notice here on the mechanical power, first motor start, we step up to here. Second motor start, we step up to here. Third motor start, yes, we're at roughly on the purple 72%. If you look at the purple one, it's at 11.3 seconds, it's 0.719. So we're about 72% of the capability of the machine. Okay, so that's a sequence. Now, to show this a little bit more clearly, since we're doing 3 of these back to back, this looks a little messy. If we were to do one motor and sequence it all by ourselves, and I have that here, drop util, start M4, it becomes a little more clear what's happening. Voltage dips, whoops, let me zoom back out again. Voltage dips, motor finishes starting, voltage overshoot, and recovery. So you can see the response of the AVR and its tuning at that point. So that's a quick thing on motor sequence and generator voltage overshoot. How about automatic transfer? I'm going to reset my simulation. And what I'm going to do to activate an automatic transfer over here is I'm going to fault this bus. To fault a bus in dynamic stability, you double click on the bus. To open or close a breaker or switch, you double click on the breaker or switch, and it will run a simulation. We'll run a simulation when we double click on the bus. I'm going to fault here. And what we're going to see happen is if we were to look at plots 3 and 4, I'm going to bring the plot window up now. We see we had a fault condition that was, this is the voltage here. The bus voltage went down to 0 very quickly. Let me zoom in. There we go, 0.027. It almost collapsed. Some current coming out of the cogen unit, Some acceleration. Speed is going up because we can't deliver the power because we collapsed the voltage on the bus, so the unit's speeding up. And then we see that, remember I talked about the AVR, how if it has an amplifier within it that basically is supplied by the terminal voltage of the machine, our field collapsed in this case. So you can see all of these results. But now we want to see how did the automatic transfer go over and affect the cogenerator. Well, I happen to have that here in plot 4. And here I've plotted the terminal voltage, current, speed, mechanical power, and field voltage of the cogenerator. So since it's just a static load, it's not a motor, we had an automatic pickup of the load. The current steps up. We can see the voltage dip and recovery very quickly. We can see the isochronous governor dip in speed, right, because you threw the load on, and then we have a full speed recovery within just a few seconds. We can see the field voltage response as well, being very, very quick. Within 3-4 seconds, it's able to pick up all the load. Obviously, we didn't overload the machine, right? Didn't overload it. Now, I see a couple questions popping up, and don't know if I can get to them. And I really, boy, they're hard to read on this little control here. I will try to take a look at them after I'm done. And so I'm trying to get this in as fast as possible for everyone. So I'm not going to be able to get to your questions, but if you put questions on there, I'll definitely respond to you, okay? And there we go. Now, one place I really would encourage someone to look when they have dynamic stability is the message log. In the message log, we have every event, every device that's changing state of some kind and being affected with some type of a trip action or some type of a limiting condition being shown here. And so we can see very clearly that we put a fault on the bus, faulted, transformer 5 primary was faulted. We start running our simulation. Oh, we have contactors picking up. Contactors picked up. So not only are we looking at an automatic transfer by the ATS, but we have a lot of other things happening. Low voltage breaker picking up on overcurrent. We have relays picking up on overcurrent. Here's our automatic transfer switch picked up on the undervoltage. Maybe, oh, this was due to motor contributions because it reset very quickly. So the motor contribution came, it went into a pickup condition, and then it reset its condition. We have a fuse that started to do something from a motor contribution. The contactors reset. So we're not going to trip off those contactors on those motors in this case. That's interesting to know, isn't it? Wouldn't you want to know that if you have a fault on one part of your system, whether or not you're going to drop out contactors on motors? In this case, they reset because the fuse cleared so quickly. Here we go. We're going further, more things happening, more things resetting. Finally, automatic transfer switch tripped on undervoltage. Now it's waiting for transfer. After the time that's specified in the stability data for the ATS, we transfer. And you just double click on an ATS and look under stability tab. You can see the different parameters that allow you to delay. Obviously you have to wait for the generator to spin up, and once the generator has spun up, then you transfer. And so you have to include that delay here for the ATS. So in this one case, I've done motor starting. I've looked at response of the generator excitation system. I've been looking at motor sequence starts. What else have I done? I've done an automatic transfer. I've looked at the generator voltage overshoot. Well, how about a couple other really interesting things that really a good surprise to find out in here? And that is, how about knowing how far a relay or a fuse went during an event? So I have a case here where I'm going to fault bus transformer primary 4, or transformer 4 primary. And basically, this overcurrent relay is going to open this breaker. So it did its job. Notice at the end of the simulation, oh, by the way, I'm going to reset. Breakers, switches, they'll show a symbol. If you fault here and a device clears, it'll say this went from closed to open. So that's what that means. So everything's dead here on the bottom. But what's interesting, if you pan over to the left, you'll notice that these contactors dropped out on these motors. Yes. So the extra time it took to clear the fault, we tripped off motors on contactors. Now, how about seeing what else happened? Wow. I think we came pretty close to tripping our generator off. R9 relay reset at 95.98% of travel. I think you would want to know that. Now, note here, you may not see this on a time current curve. Just understand, we are simulating the decay of currents in motors and generators in full detail. So you're going to see a lot more response. I mean, you might have actually seen a trip in a TCC, whereas here we're saying, well, we just squeaked under, or maybe we were a little better off than we thought. Okay? So, boy, relay 9, I believe, if we go up here, that's this one. So we may want to check our selectivity and maybe go over our protection scheme in a little bit more detail to make sure that, yes, indeed, we're tripping off devices in proper order. Okay? So how about fuses? I'm going to come down here now. I'm going to fault the MCC by double-clicking on it. Reset my simulation, double-click, and run a fault. In this case, we have a relay on this medium voltage bus tripping this medium voltage breaker. Notice the fuse didn't open, but how far did we get? Oh, relay R9 again, 79%. And look here, fuse, FS3. Fuse reset at I squared T equals 73.97%. So that means, wow, we may have fatigued this fuse slightly. I mean, I personally think if you're up in the 80 to 90% range on your I squared T, the amount of energy you dumped into that fuse during a fault condition, it's probably fatigued. And that means next time it's not going to blow in a consistent fashion. It's probably going to blow sooner. That's definitely something you would want to keep track of, and we allow you to do that here in the dynamic stability package. So, relay trip percentages, fuse. How about response to sags? So I have my system. I'm going to reset. And notice I put some additional components up here on the utility. What are we running? 1058. I'm almost done. Just got a couple more things. So if we were to have a sag up here, basically I put in a 6-cycle, 3-cycle. I'm using these devices to trip off at a given time interval, and I added some impedance in here so I could fault the bus. So if I have a 3-cycle sag, what's interesting is in this case, my system hangs together. Except for these guys went from closed to open. I had some contactors drop out. What would happen if I had a 60% 6-cycle sag? I drop out even more. So you can run that in your facility and check and see what the condition is after an event to see how you're responding and also how your generator is responding. Because in plot 3 here, we have our cogen unit. We can see how low the voltage went on 13.8 kV bus, how long it stayed there, and we can look at the total response. Okay, one last thing I'd like to show you. For those of you who are involved in arc flash studies, okay, one of the features in dynamic stability is the capability of simulating arc flash in real time with decaying currents from sources like generators and motors, with all the real-time action of protective devices, just as you have seen so far. I'm going to reset, go to my dynamic stability options, go to arc flash, and check. Use arc flash simulation for faults. Notice I've got 100%. Let me look at that again. I've got 100%. So in the short circuit and the arc flash analysis in EasyPower, it automatically does 185. 100%, then it checks the 85% arcing current as well. We don't do that here. You have to change it because each one of these runs is a full simulation. So first we look at 100%. Now we're fault 13.8 kV bus, and we're going to see in the auto plot that it's not quite as just going and getting a current, looking it up on a TCC, and figuring out how much energy you're going to have. Here we see that we have decay of generator and motor contributions. This little glitch here, I'll tell you, is the motor contactors dropping out. Then we have the cogenerator tripping. So we have the combined cogen and utility current. Then we have a trip of the cogenerator. And then we have the leftover current from the utility. And so you can see the slope changes on the accumulated energy. In the message log, we give you a summary at the end of the simulation. IBF scale 100%, 5.4 calories, arc flash time, the boundary, and the PPE level. What would happen if we were to change this to 85%? Wow, significantly different result. Different tripping time. Oh, let me do that again. Completely different behavior. Much different due to, you can actually see the AVR response in here. Look at that. You can see the AVR affecting fault current. And then it trips only briefly and then goes off. So I didn't want to necessarily say it's going to be one way or the other, but definitely wanted to show you that there is a difference due to the real-time response. The real-time response of the network is going to tell you indeed how everything will respond to an arc flash condition. And that's what we see here. For this particular case, we have a lower 4.6 calories per centimeter squared when we're at 85%. A little bit, when we're at the 100%, this was 5.4, if you remember correctly. So that's our webinar for the day. I really thank you for joining me. I hope this has expanded your knowledge into what can be done with the dynamic stability tool. Dynamic stability is probably one of the things that is used the least. I honestly, in EasyPower, it's used the least. I don't really understand why, except for maybe it's the data thing. You know, maybe that's one of the key things. That's the quandary. It's the data thing. I hope with the software that, with the features that we've put in here, and also with the large data set in the library, that will make this easy for you to do so that you can use dynamic stability in its strength. Thank you very much. Have a great week.